I would suggest that you pause the video and try these two warm-up problems. So hopefully these were the answers that you got. Remember, when you're solving for the variable n, I first moved that a over to the other side, then I divided by d, and then I finally added the 1. In the second one, I sketched a picture to help me out. I made x represent the width, and then 2x plus 5 then became the length. Perimeter means you add up all the sides, and in a rectangle, opposite sides are congruent. And then I made sure I clearly labeled what the length was versus what the width was, and I put my units with it. Today, we're going to continue with section 1.6, which once again was all about other types of equations. So today we're going to look at equations with rational exponents, so basically fractions as exponents, and we're also going to solve equations that have absolute values. So let's start with rational exponent equations. So in lesson P.3, we talked about the definition of rational exponents and how they relate to radicals. So remember, a to the m over n power is the same thing as the nth root of a raised to the power of m. So for example, say we have 3 times the 4th root of x to the 3rd power minus 6 equals 0. It's the same thing as 3 times x to the 3/4 power minus 6 equals 0. All right, here are steps in order to solve these rational exponent equations. We're going to isolate the expression that contains that rational exponent. So just like we've done in the past, like when it was x squared, we had to isolate it by itself. Well, now if we have like x to the 1/3 power, we have to isolate that by itself. We'll raise that, we'll raise both sides to the reciprocal of that rational exponent. So remember, if we have 1/2, then the reciprocal is 2 and vice versa. All right, so assume that m and n are positive integers. Okay, so we're dealing with positive exponents. M over n is also in lowest terms, so it's already as simplified down as possible. K is representing a real number. So if we ever have our value of m, so the numerator of that fraction of our exponent, if it's an even number, then notice that when we raise it to the reciprocal, it becomes n over m to both sides. And so because we have an even exponent in our denominator, that became our index. So like if it was a 2, it's basically like you're taking the square root. Well, remember, when you take the square root, you have both a positive and a negative answer. So that's why there's that plus or minus sign in front of the k. If m is an odd value, then when I raise it to the n over m power, that now tells me that m is in my denominator. M is an odd number, so it's like a cubed root or a 5th root. And so we're not going to have that positive or negative sign in front. All right, so let's solve the equation and then we'll check our solution. So if we have 5 times x to the 3/2 power minus 25 equals 0, well, remember, our first step is to isolate that exponent or that term that has the exponent by itself. So that means we have to add the 25 first. And then we still have a number on the same side as x, so I'm going to divide both sides by 5. So now we've isolated it, and it's x to the 3/2 power equals 5. So remember, now that I have that by itself, x to the 3/2 power, I have to raise it to its reciprocal, which would be to the 2/3 power. But because it's an equation, if I do it to one side, I have to do it to the other. Notice that my denominator now, when I did that reciprocal, it's an odd number. So it just becomes x on the left because remember, a power to a power means multiplication, and the whole point is that those reciprocals turn into the number 1. Now when I have 5 to the 2/3 power, I could, I guess, technically leave it like that, but it would be a good idea to make sure you can try to simplify it. So rewriting it as a radical will just help us better see if this is something that can get simplified. So remember that denominator becomes the index, the numerator is what it's being raised to. So now notice we have the cubed root of 5 being squared. Well, notice how the cubed root of 5, there's no number that multiplies by itself 3 times to get 5. So I'm not going to be able to simplify that any further. Another way we can think of this is if I had it written like this, where the 5 is being squared, right? So technically, if you want, you can square that 5, and then it's the same thing. It's the cubed root of 25, and you can't find 3 of the same numbers that multiply to get you 25. All right, so then if we're checking our solutions, we're going to go back to the original equation. So we've got 5 times. Now I can honestly use any of these values. This is equivalent to this, which is equivalent to this. I guess this is the same. So honestly, you can check it with any of those. So if I go back to like this one right here and I say 5 to the 2/3 power represents x, and that's raised to the 3/2 power. And then I say minus 25 equals 0. Notice that power to a power, once again, those are reciprocals. That just turns into a 1. So that means that that's 5 times 5 minus 25 equals 0. So 25 minus 25, that does equal 0. That checks out. I'm just going to circle this one as my final answer, but it was the same thing. They were all equivalent. So that'd be my answer. Okay, same idea. Let's go ahead and look at x to the 2/3 power minus 8 equals negative 4. So we start off by needing to get the x by itself. So I'm going to add 8. And so now I have x to the 2/3 power equals 4. Okay, so now remember, once I have that isolated, I'm going to multiply by the reciprocal, and that becomes the exponent. So the reciprocal, the exponent, is now 3/2. Okay, so the whole point is that it just becomes x, and now we have 4 to the 3/2 power. That can get simplified. Remember, the index then is 2. So I can simplify this down. Notice that the square root of 4 is 2, and 2 to the 3rd power is 8. Okay? So then if I wanted to check my solution, notice that my power of m, though, got moved down to the denominator, and notice that that's an even number. So remember, we technically have both a positive and a negative here. So I have both positive and negative 8. Okay, so those are my potential answers for x. Now let's check our solution. So let's check when x is a positive 8. So if I have 8 to the 2/3 power minus 8, and I want to know, does that equal negative 4? Okay, well, 8 to the 2/3 power is really the cubed root of 8 quantity squared. And notice that the cubed root of 8 is really 2, and 2 squared is going to give me 4. Notice that 4 minus 8 will give me negative 4, so that does check out. If I was to check then x equaling negative 8, we have negative 8 to the 2/3 power minus 8, and once again, I want to know, does that equal negative 4? Well, we have, once again, the cubed root, but this time it's negative 8 quantity squared. When I take the cubed root of a negative, I'll get a negative. That becomes negative 2. But notice how it's becoming then that quantity being squared. So that does still become 4, and 4 minus 8 does give me negative 4. So that's why it checks out that when you have your m value when it's an even number, that's why you have 2 solutions there. So both a positive and a negative 8. Okay, so please pause the video, see if you can come up with your solutions. All right, so notice that we already had that exponent isolated by itself, so I raised both sides to the reciprocal, and because we ended up with being able to simplify that into the number 4, when I subtracted the 5, it gave me one answer. Because my value of m was an odd number, there was no plus or minus sign in front of it, and I checked it out and it worked. All right, so let's move on to equations that now have absolute values. We have seen absolute values of x, which are denoted like that. describing the distance of x from 0 on a number line. So that's why whenever you take the absolute value of a number, regardless if that number inside the absolute value is positive or negative, you're going to get a positive answer because we're describing distance, and you can only describe distance with positive values. So therefore, to solve an equation of the absolute value, if we have that absolute value isolated by itself and it equals c, it's equivalent to then just x equaling c or x equaling negative c. So whatever is inside the absolute value, if it's isolated by itself, you set it equal to the positive value of c as well as the negative value of c. All right, so here are the steps that I kind of just described. We have to isolate that absolute value by itself. So anytime there's a number outside of the absolute value on the same side, move it by adding, subtracting, multiplying, or dividing first. Then we'll create our two equations based off of that definition, where remember, we'll have it equal both the positive and the negative value of whatever the number was that was isolated by itself. However, when you start the isolation process, if you end up with the absolute value equaling a negative value, well, you can't do that because, like I said, when you take the absolute value of a number, it's only going to end up being a positive value because we're describing distance. So if you have an equation where the absolute value of a number equals something as a negative number, well, then right off the bat, we know it's the empty set. All right, we're going to solve, and then we'll indicate whether or not there are no solutions. So notice that in this case, the numbers that are on the same side of x are all inside the absolute value. So the absolute value is isolated by itself. The number that it equals is a positive number, which tells me that right off the bat, there will be a solution. And so I'm going to take what was inside the absolute value, and I'm going to create two equations. I'm going to take that, and I'm going to set it equal to that 5. But I'm also going to take this 2x minus 1, and I'm going to set it equal to negative 5 because I have to set it equal to the opposite value. And now we're going to be able to start solving for x. So I'll add 1. That gives me 2x equaling 6. I'll divide both sides by 2. And so one of my answers is 3. Same exact steps over here. I'm going to add 1. That gives me then 2x equaling negative 4. I'll divide by 2. And I get negative 2. So once again, you can always verify this to yourself that you did it correctly by substituting them in. If I substituted 3 in, 2 times 3 is 6, 6 minus 1 is 5. The absolute value of 5 will equal 5. If I substituted in negative 2, 2 times negative 2 is negative 4. Negative 4 minus 1 is negative 5, but the absolute value of negative 5 is positive 5. So that's why these two are my answers. Okay, and the next one, notice that we are dealing with some numbers that are outside of the outside of the absolute value, but they're on the same side. So I first have to isolate the absolute value. So I'm going to add 20 over to the right. That gives me 4 times the absolute value of 1 minus 2x, now equaling positive 20. I still don't have that absolute value by itself, so I had to divide by 4. So now I have the absolute value of 1 minus 2x, and that equals 5. So now that I've isolated that, notice that I have a positive number for what that absolute value equals, which tells me I will have a solution. So I take, once again, what was under or inside the absolute value, and I set that equal then to 5. And I also set that equal to the opposite of 5. So I'm going to have to subtract 1. That gives me negative 2x equaling 4. I'll divide by negative 2. And so one of my answers is negative 2. Over here, same steps. I'll subtract 1. Negative 2x is going to equal negative 6. I'll divide by negative 2. And I get 3. So I know you probably won't, but both my answers from both these problems ended up being the same. Obviously, that's not always going to be the case, so just be very careful with your algebra. Okay, I would suggest that you pause the video and try solving this. Hopefully you noticed that when you were isolating the absolute value by itself, the first step you had to do was subtract the 6. And so right off the bat, that isolated the absolute value, but it equaled a negative number, which once again is something that we can't have. And so we didn't even have to go any further. That was the empty set. It was no solution. Okay, so those were our other equations with rational exponents and absolute value.